What is topology? See, in graduation level, we learned about point set topology. We deal with real numbers, one-dimensional space. In metric space, we moved to higher dimensional space. We deal with open ball instead of open interval. Topology is higher dimensional geometry. Here, we will see the property of connectedness between geometrical shapes, right? Suppose X is any non-empty set. X be any non-empty set. Okay. Now, what is Px? Px is the power set of X, right? Power set of X. That is the collection of all subsets of X. Now, what is topology? Any subset of Px. That is, now what is topology? Topology, tau is any subset of Px. It is said to be topology when tau satisfies some condition, number 1, number 2 and number 3. Number 1, null set and the whole set both are belong to tau. Number 2, any arbitrary union of collections of tau is in tau. That is, if we take A alpha from tau, then the arbitrary union of this collection again in tau. And number 3, if we take any two elements, say A1 and A2 from tau, then their intersection is again will be in tau. So, any collection of subsets of X, tau, is said to be topology if these three conditions are satisfied. Number 1, empty set and whole set X is in tau. Number 2, if we take any elements from tau, then their arbitrary union is in tau. And number 3, if we take any finite number of elements from tau, their intersection again is in tau. Then we say tau is topology. Fine. Now see, if tau is topology, then it satisfies three conditions, right? In my previous video, if you remember, I have shown some property of open sets, right? Can you remember it? You can see the exact properties are these three conditions. What they are? They are phi comma x is in tau. Number 2, arbitrary union of any elements of tau is in tau. Number 3, if A1 and A2 is in tau, then their intersection is in tau. So my friends, the elements of topology are called open sets. Fine. The elements of topology are open. Then you can compare these three conditions with the three properties from metric space. Here I write the elements of topology are open. So tau is topology, therefore phi and x are open, right? Number 2, A alpha is from tau, that is A alpha is open. Okay. Therefore, here you can see any arbitrary open set is open because it is in tau. And number 3, A1 and A2 is from tau, that is these two are open set and their intersection is in tau, that is it is also open, right. So, finite intersection of open set is open. Okay. Now see some example. Say x is given by a comma b comma c and topology tau 1 is given as phi x singleton a singleton b and AC. This is number 1. Number 2, tau 2 is given by phi x singleton A singleton C. Okay. Number 3, tau 3 is given as only phi and x. Number 4, tau 3, I said it, say px. Now I have to find which one is topology and which one is not. Now we have to find which one is topology and which is not. See, number 1, tau 1 is phi x singleton A singleton B and AC. If you see the definition of topology, then you can find that the number 1 condition is phi and x is in tau. So here phi and x is in tau, right? Number 2, if we took any two element from tau 1, then its union has to be in tau 1. But see here, if I took these two elements, say singleton A and singleton B, then their union is A union B, okay, which is not in tau 1. So number 2 condition is not holds. So it is not a topology, okay, it is not a topology. Number 2, if we check here, phi and x is in tau 2, but if we take these two, their union is not in tau 2. So it is again not a topology, right? Number 3, here phi and x is in tau 3. If we take their union, so phi union x is x, it is again in tau 3. So number 2 is hold. And for number 3, if we take their intersection, it is phi, and phi is again in tau 3. So it is a topology. For number 4, here tau 4 is given as the power set x. That means it contains phi capital X singleton A singleton B singleton C AB BC AC, right. So phi and x is in tau 4. If we take any 2 or 3, any arbitrary collection, say A, B, C, their union is x, it is here. If we take B and C, their union is BC, it is here. If we take A, C and AB, their union is x, it is here. If we take A, C and C, their union is C, AC, it is also here, Px, right. If we take finite number of elements from this and take intersection, it is also in Px, because Px is the power set. So it is a topology. Now, one important definition from topology is comparable topology. Suppose tau 1 and tau 2 be two topologies and tau 1 is contained in tau 2, then tau 1 is coarser and tau 2 is finer topology, right? See here, tau 2 contains tau 1, so tau 2 is finer than tau 1 and tau 1 is contained in tau 2, so tau 1 is coarser, or we can say smaller than tau 2, and it is finer or bigger than tau 1. And if we can write two topologies like this, tau 1 contained in tau 2 or tau 2 contained in tau 1, then tau 1 and tau 2 are called comparable topologies. Okay. And if we cannot write tau 1 and tau 2 in this form, that is neither tau 1 contained in tau 2 nor tau 2 contained in tau 1, then these two topologies, tau 1 and tau 2, are called incomparable topologies. This is comparable, incomparable, right? Now we see some types of topologies. Number 1, discrete topology. In example number 4, that is when I deal with tau 4, which is power set of x, this is a topology, right? We just proved it. It is a topology. This topology is called discrete topology. This topology is called discrete topology. Okay. Indiscrete topology. In example number 3, that is I took tau 3 as phi and x. This is topology, right? We have seen it. This topology is indiscrete topology. This is the smallest topology of x and this is the largest topology of x. Sometimes it is called as trivial topology. Okay. Cofinite topology. Now what is cofinite topology? If A is any subset of x, then tau, I write here cof. Cof means cofinite. Okay. Then tau cof, which is collection of subsets of A. Okay. Tau cof is a topology. We denote cofinite topology with this term tau cof. Okay. So tau cof is cofinite topology. Cofinite topology if the complement of this subset A, that is x minus A, is either finite or all of x. Okay, that is tau of, which is the collection of subsets of A, where A is any subset of x, is said to be cofinite topology if the complement of A is either finite or all of x. That complement is finite, so it is cofinite. Okay, co means complement, finite you know what is the finite set. So the complement of A is either finite or all of x, that is tau of equal to A such that A complement is finite or all of x. We can write it as phi comma x comma A such that A complement is finite, right. See, A complement is all of x, that is A complement is all of x, that is A is phi, right. From this we can say it. Okay, A complement is finite. If we take A is whole x, then its complement is phi, which is finite. So x is here, right. So we may write tau of as like that. Now co-countable topology. We denote co-countable topology as tau coq. Co means complement and C means countable. Altogether, this is co-countable. Now, what is co-countable topology? Similarly, you can write tau coq is collection of subsets of A, where A is any arbitrary subsets of x. We say this is co-countable if either A complement, that is x minus A, is countable or all of x, that is tau coq is A such that A complement is countable and all of x. We can write this as phi x A such that A complement is countable, right. Similarly, you can write this as phi x A such that A complement is countable. Now, suppose you have a question, rational number q is open or closed in co-countable topology. Okay. Now, what is co-countable topology? We know tau coq is said to be co-countable topology where tau coq is collection of subsets of A if A complement is either countable or whole of x. Now, co-countable topology is defined on set of real numbers R. Here Q is countable, right, and Q complement, that is the set of irrational number, it is uncountable. Okay, it is uncountable. Since it is uncountable, so set of rational number is not in tau coq. That means it is not open. Okay, since rational number q is countable and its complement is uncountable, so q is not in tau coq. Fine. And since q is not in tau coq, so q is not open. So is it true that q is closed? We know q is not open, but is it true q is closed? See, what is closed set? The complement of open set is closed set. Okay, the complement of open set is closed set. To show q is closed, we have to show its complement is what? Open. Its complement means qc, right? And qc is the set which is in tau coq. Why? Because its complement means set of rational number, okay, and it is countable. Since it is countable, so qc is in tau coq. That means it is open, and we know that since it is open, so its complement, which is q, is complement of open, that means closed. Therefore, the set of rational number q is closed in tau coq. Similarly, you can check q is neither open nor closed in tau coq. I give it as an homework. Please do this. If you are not able to do this, let me know in comment box. I will show it in my next class. Thank you.